Good afternoon, everyone. The topic of this session is hydrogen production, transportation, storage, and distribution technologies. Currently, hydrogen production is mainly through SMR technology, where a lot of CO2 emission also takes place. To take care of this part, we are trying to move towards green hydrogen, where hydrogen production will be through electrolyzer or through biomass. The, once production through electrolyzer and biomass, then source will be different and consumer may be different. Because of that, all this topic, transportation, storage, and distribution technology, it got significance. It has more importance also because in future, hydrogen is going to be a carrier for energy sources, and we are trying to move towards from hydrocarbon economy to hydrogen economy. With that, I would like to invite Dr. Klaus Brun.
All right, can you hear me? Oh, yeah, because I couldn't hear anything. But okay, I was told that I have 14 minutes, and if I go any minute over that, I'll be cut off. So I'm going to go fast. I think I have a clicker here. Okay, well, I skipped the first slide already. This presentation is basically about hydrogen compression, the challenges of hydrogen compression, and let me skip the advertising real quick and go to the first slide. Really, if you look at the world energy right now, especially from a compression perspective, there are three things that are going on. We're seeing one mega trend, which is LNG, right? So the world is changing toward transportation of natural gas, and that's primarily driven by geopolitical changes that have very little to do with ecology and anything. But natural gas is also somewhat of a transition fuel for decarbonization because it does have a relatively low carbon to hydrogen ratio. The other thing we're seeing is a trend toward hydrogen, because hydrogen is obviously a carbon-free energy carrier, and that's what I'll be talking about today. And finally, another interesting topic, but I won't spend time on that today, is carbon dioxide, because you really need to transport carbon dioxide if you want to decarbonize the existing fossil fuel energy infrastructure, which is still responsible for approximately 80 to 85% of all the world's energy production. So you really have to deal with carbon dioxide and its sequestration also if you want to really decarbonize the energy infrastructure. There's all kinds of colors of hydrogen, rainbow of hydrogen. Everybody has different colors. From a decarbonization perspective, the only two that really matter are green hydrogen, which is hydrogen produced from alternative energy sources and curtailed energy. And then there's blue hydrogen, which is really fossil fuels converted into hydrogen, and then the CO2 is sequestered in some way. If you look at the logistics of that, we don't need to even worry about blue hydrogen here, because blue hydrogen doesn't really require hydrogen compression and transport, right? For blue hydrogen, most likely you're going to make your hydrogen at the site where you're going to need it. So there's not a lot of compression required for that. Green hydrogen, then, on the other hand, needs to be transported by pipeline or by some other means from where it is produced to the end user side. And for that, if you want to transport anything by pipeline, you either need a compressor if it's in gaseous phase, or you need a pump if it is in liquid phase. So you really have two options from a transport perspective if you look at green hydrogen. One is to blend the hydrogen into a natural gas existing infrastructure, and the other one is to just develop your own hydrogen infrastructure. And both of those can be considered. The only issue with that is if you go with option A, which is blending your hydrogen into an existing natural gas infrastructure, then you run the risk that your hydrogen will end up behind the city gate in the domestic distribution system. And there is very little data available in the world on how safe that is. Whereas you can really make your industry, your refineries, your power plants safe for hydrogen operation. It is very challenging to make your domestic distribution network and domestic end users safe for any amount of hydrogen blending. On the other hand, building a hydrogen infrastructure, meaning pipelines dedicated to hydrogen, is very expensive and very, very challenging. So these are the two options. From a compression perspective, there's really a number of compression applications. One is you got to get your hydrogen into the pipeline, right, from wherever you're getting it, most likely an electrolyzer. If it is for a blue hydrogen, then it would be a steam reformer, gasifier. And so that really drives your suction pressure of your compressor. Your discharge pressure is probably somewhere around 1400 psi, 1500 to 100 bar or so in that range, and that drives your compression ratio. Hydrogen is a gas that is very, very difficult to compress, and I'll talk about that a little bit because it is a very, very light gas. Hydrogen versus natural gas. We're very familiar with compressing natural gas. There's natural gas pipeline infrastructure in the world. If you look at hydrogen, it's not just a very different gas. You look at the mole weight, density, speed of sound, Joule-Thomson coefficient, all of that kind of stuff. It's very different. But it also is a gas that is somewhat unsafe. It has a very wide flammability range versus, for example, natural gas. It is a gas that disperses very easily, and it has a very low ignition energy. So from a safety perspective, you also have to worry about hydrogen. You don't just have to worry about from a thermodynamic of compression perspective, but also from a safety perspective. So these are really the challenges of hydrogen compression. It's a light gas, and I'll talk about that a little more, which means you're really getting a very low pressure ratio for your compressor per stage. I'll talk about the thermodynamics just a little bit. Sealing. Hydrogen is a very, very small gas, small molecule kind of gas, so any kind of static and dynamic sealing, you get much higher leakage with hydrogen than with any other gas. So you have to worry about sealing, and obviously you want to keep your hydrogen inside because, as I mentioned before, it is very, very flammable. Materials and coatings. With hydrogen, you have to worry about hydrogen embrittlements. You can apply some coatings, but coatings are generally not a long-term solution for a hydrogen embrittlement issue because eventually your coating will spall away or wear off. And then safety, as I mentioned before, it is very explosive as a gas, and so you have to worry about that. From a thermodynamic perspective, and I promise that's the only equation I have here, but from a thermodynamic perspective, hydrogen gives you a much lower pressure ratio than, let's say, natural gas or carbon dioxide. And it comes down to basic physics. I don't want to get into the physics, but let's say you have a compressor. That's a 10,000 RPM compressor that's about yay big and yay big, and you stick natural gas in that. You will get a certain amount of head. If you stick hydrogen in it, you will actually get the same amount of head. Everybody thinks, oh no, you get a lower head. That's not true. You get the same amount of head because if you look at the equations that drives the physics here, which is all our turbo machinery equation, there are no physical properties in that equation, right? But if you convert head to what we really care for, which is pressure ratios, compressors are meant to make pressure, right? That's why they're called compressors. When you look at head to pressure conversion, that's where you're actually getting a very, very low ratio. And that's driven by that last equation that I've down there. And that's really driven by the specific heat of hydrogen. Hydrogen has a very, very high specific heat. Therefore, you get a very low compression ratio in hydrogen versus, let's say, natural gas or carbon dioxide. What does that mean? That means if you want to, let's say, have a compression ratio of 3:1, which is not very difficult for, let's say, natural gas. One compressor body, you could do that. With hydrogen, you need 4 compressors with something like 40 or 50 stages. Right? So the challenges are basically, from a thermodynamic perspective, that if you want to get the compression ratio that you need, which is something like 2, 2.5, or 3, you need either lots of compression stages, that's one solution, right? So many compressor bodies, or you can increase your rotational speed of your compressor, right? You can just basically run your compressor faster, gives you more head, and therefore it gives you more pressure ratio. Or you can increase the diameter of your impellers. That's basically the same approach because you get a higher tip speed, therefore you get a higher head, therefore you get a higher pressure ratio. Or, as I mentioned, you can increase the compression stages. Compression stages cost money, and so really the long-term solution is to go a higher speed. As a quick aside, if you, for example, blend hydrogen into natural gas, this is what you get. If you put, for example, 20% hydrogen into natural gas, your compressor operation is very similar to that of running pure natural gas. But let's say if you put 40 or 50% hydrogen into natural gas, you're seeing already about a doubling of the power. If you go to 100% hydrogen, you see a very high amount of power required. That also tells us that hydrogen compression is very, very energy intensive. It is much easier and much lower cost from an energy perspective to transport natural gas, carbon dioxide, or any heavier gases than hydrogen. So that is something that you need to take into consideration, because transporting hydrogen is not just difficult from a safety perspective, but it's also energy intensive. So what are your other options? You can increase the tip speed of your impeller, right? You can basically run your impeller twice as fast. So that gives you more head, right? And so, for example, if you have a pressure ratio of 2.5, like it is shown in this slide, which would be, let's say, electrolyzer to pipeline, in a normal conventional impeller running at a tip speed of 1,200 feet per second, that's about 350 meters per second, that gives you a requirement for 4 or 5 compressor cases, which is a lot. Let's say you double that speed and you're trying to do the same pressure ratio. That means you end up with only about 10 impellers. You could squeeze theoretically 10 impellers into a single compressor casing. Reality is you're running so fast that for rotor dynamic reasons, you're still going to need 2 cases, because you're going to have a shorter shaft to avoid rotor dynamic issues. But that's a significant improvement of the issue. So that's a potential solution. But if you run your impeller faster, you're going to get higher stresses, and you're going to run into stress limitations. So how do you get there? You need to look at the different materials. Most current impellers are made of some kind of steel, stainless steel, but that's not going to work, because your material is going to be able to handle higher stresses. What you're really worried about is your strength to density ratio. It's not just the stresses, but it's the stresses that get generated by the hoop stress that is generated due to the weight of the material. So aluminum is an option, because aluminum is nice and light. So that's probably a possible material. We've been working on continuously wound carbon fiber impellers. That's another potential solution. Advanced ceramic materials, we've been working on that. Those are all potential solutions to basically run your impeller faster so that you can get a higher head. Some people say, oh, you should be running with titanium, or you should be running with high nickel alloys. Unfortunately, those materials tend to have very bad characteristics from a hydrogen embrittlement perspective. You really don't want hard materials. You want relatively soft materials that are strong and light. The other thing you can talk about is putting hydrogen coating. Just use the same base material, avoid hydrogen embrittlement by using coatings. Okay? That is a solution. The only problem with coatings in general is that they don't provide a long-term answer. All coatings will eventually come off. There's spallation, there's wear, there's degradation of your coating. All of the coatings will eventually disappear, and so that you're going to end up with hydrogen on your base material, and your machine will fly apart. So it really isn't a long-term solution for a machine that's supposed to run for 5 to 10 years. And then you can design your impeller in such a way that you have higher head per head. That gives you a lower efficiency. So you're sacrificing efficiency for head and the impeller, but it is certainly a possible solution to make your impeller blades more radial. Therefore, you get more head, and therefore you get more efficiency. Those are all possible solutions. Now, I've kind of poo-pooed all over hydrogen. We've been making hydrogen compressors for 60 or 70 years, right? For refinery applications, they work. So yes, there are significant challenges in hydrogen compression, but solutions do exist. They're just not very easy. Okay? One of the solutions that is currently technically available is what we call our flex-up compressor arrangement. It's basically a conventional compressor arrangement with 4 compressor bodies all set up on a single gearbox, or a bull gear, 4 pinions, running at a relatively high speed. And so in this kind of arrangement, you manage to get many, many compression stages into a relatively small footprint, which is easy to operate and easier to maintain. So that's currently available technology. This is not stretching technology, because you're basically still running at tip speeds that are proven tip speeds for compressors. And this is a solution that you can get right now, and that works. I'll skip some of this. Another solution is to go with really, really high-speed impellers. And so you could, for example, go integrally geared machines. Again, you're looking at this particular case, you're looking at a bull gear with a bunch of pinions, and you're looking at an 8-stage or 6-stage, depending on what you're trying to do, impeller. In this particular case, you can run relatively fast with a driver that's relatively slow because you have a single gearbox that allows you for a very high ratio. So that's also a technical solution that's viable. I'll skip some of that. A lot of people talk about reciprocating compressors for hydrogen. Yes, they do get a good compression ratio. They do not require less power than a centrifugal compressor. The thermodynamics are the same. But now you have to worry about pulsation control, lube oil leakage into your hydrogen, material limitations, reliability, and power requirements. So reciprocating compressors are usually not an answer for large hydrogen flow applications. So basically your viable technologies are for low compression ratios, a single barrel type compressor, or you can run that a little faster, call it a high-speed compressor. If you go to higher compression ratios, you would have to go to something like the flex-up arrangement that I mentioned earlier, or if you really want to get into high stuff, then you need to look at single or multiple integrally geared compressor solutions because you really need high-speed machinery. Just kind of a quick aside, you don't just need compressors, you need all kinds of other machinery. You really need an entire portfolio for decarbonization and for sustainability. So that's what we do. We build very, very large machinery. So that's my little advertising pitch at the end. And with that, I'm done and I stayed within my time.
Thank you, Dr. Klaus Brun. Now I invite Ms. Vijaya Chitti.
Good afternoon, ladies and gentlemen. It is my privilege to welcome you all for my presentation. I am Vijaya Chitti, representing Engineers India Limited. This afternoon, I would like to present about hydrogen embrittlement in hydrogen pipelines, material challenges, and its mitigation. I am associated with EIL for the past 17 years, and I am accountable for materials, corrosion, failure analysis, and corrosion studies in refineries, petrochemical, offshore, onshore, and gas processing unit. The outline of my presentation is I will give a brief introduction about the hydrogen and its transportation through pipelines, comprehensive detail about the hydrogen embrittlement, its causes, sources, and mechanism, and salient points about the applicable design codes for hydrogen pipeline. Then I will discuss about the impact of hydrogen on the pipeline steel materials. I will just touch about the integrity assessment of hydrogen pipeline. Last is a case study which I will discuss, which we have carried out for one of the major pipeline operators. Hydrogen has been championed as a vital player in the future energy mix needed to achieve net zero carbon emission because hydrogen has the potential to create limitless emission-free and efficient energy. Gaseous hydrogen is considered as a clean energy source and supply in a sustainable, reliable, and cost-effective way. In this framework, large-scale production, transportation, and storage of gaseous hydrogen will be required, and development of infrastructure of transportation and storage will be a challenging task for accelerating the commercialization of hydrogen economy. So the most efficient way to transport hydrogen is through pipelines. The cost of constructing a new dedicated pipeline will be huge, and it may take decades to complete the task. So the most economically viable option is to utilize the existing natural gas pipeline because natural gas pipelines are widely available with well-established safety procedures. As the physical and chemical properties of hydrogen vary with the natural gas, the existing natural gas pipeline may not be suitable to completely transport pure hydrogen without major modification and prior qualification testing. However, certain concentration of hydrogen can be blended with the hydrogen and without any major modifications. But before blending hydrogen in the pipeline, integrity assessment of the pipeline need to be carried out so that safe operation can be guaranteed. Let us quickly see about the hydrogen production nomenclature. Based on the processes and sources, hydrogen are classified into various colors like gray hydrogen produced from the fossil fuels, turquoise hydrogen produced from the natural gas, green hydrogen from the renewable energies, and yellow hydrogen from the grid electricity. When the carbon dioxide is emitted, the hydrogen produced is termed as the gray hydrogen, but when the carbon dioxide is captured by the downstream technologies, it is termed as a blue hydrogen. It also means that how well hydrogen contributes to the decarbonization depends on how clean and green the method of production is. The green hydrogen is a critical piece of energy transition where to achieve net zero carbon emission. So green hydrogen can substitute gray hydrogen and it can be used in various industries as a feedstock and as an energy carrier. This is a pictorial representation of using green hydrogen as a feedstock in various sectors and using energy carrier in various applications. Due to its unique characteristics like flammability, ease of dispersion, the gaseous transportation and storage of gaseous hydrogen is a challenging task. There are three modes of transportation of hydrogen like trucks, tankers, pipelines, and through shipping. Among these three modes, the most efficient way to transport gaseous hydrogen is through pipelines, but the dedicated new hydrogen pipeline may increase the capital cost. So the most economical solution is to utilize the existing natural gas pipeline. So when we are blending hydrogen in the pipeline, in the existing natural gas pipeline, hydrogen embrittlement is a dominant damage mechanism that may occur to the pipeline steel material. So let us see about detail about the hydrogen embrittlement. Hydrogen embrittlement is nothing but the loss in the strength, ductility, and fracture toughness of susceptible material. This can lead to brittle cracking and it occurs at ambient temperature. Its effect decreases when there is an increase in the temperature. Hydrogen has a tendency to segregate wherever there is a pre-existing cracks. See, the mechanism of hydrogen embrittlement is the hydrogen molecules dissociate into hydrogen atoms. The hydrogen atoms enters into the material, diffuses into the material, and it occupies the grain boundaries. The hydrogen atoms or molecules combine to form hydrogen bubbles. These bubbles act as a pressure concentrators and create pressure between the grains. So when there is pressure increases to a certain level where the material loses its ductility and eventually leads the crack to form. This figure represents the micro to macro scale propagation of hydrogen embrittlement. First, the hydrogen molecules dissociate into atoms. It enters into the lattice. It disturbs the lattice, and when there is increase in the stress, it breaks the lattice and evolves into micro crack propagation. This figure D represents the macro scale propagation. So the conditions that are responsible to cause hydrogen embrittlement are the susceptible material or the susceptible microstructure, and second is the temperature in the embrittling range. Third is the stress above the threshold value, applied stress or residual stresses. The fourth one is the critical concentration of hydrogen. So these are the four conditions that are responsible to cause hydrogen embrittlement. There are three kinds of interactions. Hydrogen interacts with the material, three kinds of interactions. First, it interacts with the surface of the material where the hydrogen molecules dissociate into atoms. The atoms enters into the molecule into the material and interacts with the bulk of the material. And hydrogen atoms have a tendency to segregate wherever there is a pre-existing cracks or any subcritical cracks. Then hydrogen atoms it interacts with the defect and changes the local properties of the material, thus causes the hydrogen embrittlement. So before blending hydrogen in the natural gas pipeline, evaluation of presence of any pre-existing cracks or any subcritical cracks need to be carried out, and if found, it should be rectified so that occurrence of hydrogen embrittlement can be reduced. So how hydrogen enters into the material? Through melting practice or through manufacturing process, through cleaning, pickling, through high temperature, hydrogen gas atmosphere, aqueous corrosion reactions, or through cathodic protection. But in the natural gas, hydrogen blended in the natural gas, it enters directly through dissociation of gaseous molecular hydrogen at the steel surface, and the concentration of hydrogen entered into the material can be determined through the Sievert's law. So there are two mechanisms to help us to explain the hydrogen embrittlement. The one is the hydrogen enhanced decohesion theory, which causes a brittle failure, and hydrogen enhanced localized plasticity, which causes a ductile failure. Hydrogen enhanced decohesion theory is based on the decohesion mechanism. Decohesion is nothing but a simple sequential tensile separation of atoms. The hydrogen atoms enters into the material, it occupies the grain boundaries, and it has a tendency to segregate wherever there is any defect. The hydrogen atoms, the combination, it weakens the interatomic bonding and decreases the cohesive energy between the grains, and the combination of the stress and the critical concentration of hydrogen is sufficient to cause a decohesion in the plastic boundary, and eventually causes a crack to occur. This hydrogen enhanced localized plasticity is this causes the ductile failure. This atomic hydrogen enhances the localized dislocation mobility of the dislocations by reducing the critical stress intensity of the dislocations. The dislocations often have a tendency to pack together, thereby increasing the dislocation density and creates the highly localized deformation region. So this it causes eventually crack to occur. So these are the two mechanisms that help us to understand the hydrogen embrittlement mechanism. So now let us see about the design codes that are applicable for the material selection in hydrogen pipelines. ASME B31.12 is a predominantly used standard for hydrogen pipelines. This standard provides about information about the material selection, design, fabrication, qualification, testing, and also gives of information about repurposing the existing pipelines, and this is applicable for above 10 volume percentage of hydrogen, and this offers two options for testing for fracture for determining the fracture resistance of the material. Option A is the prescriptive method and option B is the performance based method. So this table represents the characteristics of both option A and option B. There are other standards for use for the hydrogen pipelines. ASME KD10 is a fracture mechanics approach used to determine the fracture toughness of the material and fatigue crack growth rate of the material. IGC document published by the EGA, this recommends to use up to X52 or the lower strength materials. And API 579, this is the fitness for study assessment to evaluate the integrity assessment of the pipeline. There are two other standards from ASME, which is for the standardization of tanks, piping, and pipelines. This slide shows some of the parameters that are responsible, that are required for estimating the component evaluation in the pure hydrogen or in the gaseous blend. Parameters under microstructure like processing variables, heat treatment, welding, then chemical composition, mechanical properties, under the dissolved hydrogen partial pressure, temperature, under the stress, operating pressure, pressure fluctuations, pipeline geometry, then the thermal stresses, then under flaw severity, length of the flaw, depth, location of the flaw. So these are the parameters that are required and fed as an input to these models. From these models, we can determine the pipeline failure pressure. First, three critical parameters: pipeline failure pressure, critical crack size, and residual life of the material. So these three parameters are useful in the integrity assessment of the pipeline. When we see about the impact of hydrogen on the pipeline steel material, it affects the steel integrity of the material. It increases the fatigue crack growth rate when it is cyclically loaded. During operation, the pressure fluctuations accelerate the subcritical cracks and thereby reduces the fatigue life of the material. Second is it decreases the fracture toughness of the material. Third is it decreases the steel ductility of the material. Hydrogen embrittlement is more problematic in the high strength steels. So when we see about the fracture toughness is the material resistance to crack propagation. It is a function of steel composition, microstructure, and temperature. The fracture toughness in the natural gas pipeline with natural gas is mentioned as K1C, and in the hydrogen pipeline it is mentioned as K1H. The fracture toughness, when it is measured in hydrogen containing atmosphere, it can be lesser than 50% than the K1C. So this decrease in the fracture toughness depends on variables like the residual life, critical crack size, and the failure pressure. Then the fatigue crack growth rate in the hydrogen environment increases at a very faster rate when it is cyclically loaded. Then it accelerates the pre-existing cracks and under the cyclic stress, so thus reducing the fatigue life of the material. This fatigue crack growth rate and fracture toughness are the two important parameters that are directly used in the integrity assessment of the pipeline. So before blending hydrogen in the pipeline, we have to ensure that there are no any subcritical cracks or any pre-existing cracks. If found, it should be rectified so that the occurrence of hydrogen embrittlement can be decreased and safe operation can be guaranteed. This is the slide which shows for about the integrity assessment. API 579 can be used for carrying out the integrity assessment of the pipeline. This standard gives about the different levels of the crack assessment using the FAD methodology. It allows us to estimate if cracks can propagate from the tip of a given defect or not. So this standard can be used in the for carrying out the integrity assessment of the pipeline. Last is a case study which we have carried out for one of the major pipeline operators. Our study is to determine the material suitability and to assess the right proportion of hydrogen in the natural gas environment. We have carried out a conceptual study, and based on the study, we have allowed to blend below 10 volume percentage of hydrogen and limited up to X42 and 52 material with weld hardness of HRC 22 in both weld metal and the base metal. Our recommendations were based on the three reasons. First is ASME B31.12 is applicable only for above 10 volume percentage. So we can assume or we can predict that below 10 volume percentage there will not be any significant impact on the gas composition and also on the pipeline material. And the second reason is the effect of OBE index also shows that the impacts are very minimum, and there are widely accepted literatures which shows that the blending of less than 10 volume percentage have very little impact on the gas composition. For higher strength materials like above X52, we have recommended to carry out the laboratory testing, and the testing results, we are yet to receive the testing results from the laboratories.
Thank you, Vidya, for enlightening all of us on hydrogen embrittlement and in general material behavior in hydrogen environment. Now the next speaker, Mr. Rahul Garg.
Good evening, everyone. Myself Rahul Garg, and I represent Bharat Petroleum Corporation Limited. I'll be presenting the research work what we are carrying out our R&D center related to the hydrogen compression through metal hydrides. So the mechanical compression is a system which is being traditionally used, and the research is happening on how we can use the metal hydrides for hydrogen compression. Although there are some pros and cons of this, which we will be discussing in the subsequent slides. However, my presentation would be a bit technical, and I would try to explain the technicality in a much simpler form. So, Bharat Petroleum is working in the complete hydrogen value chain, which is starting from production and going to the utilization. For the production side, we have already worked on the alkaline electrolyzer, which we are displaying in the hall 1, that is indigenously manufactured. Now comes the compression of a hydrogen so that it could be used in a near term in all the applications. So we have undertaken a challenging research project at our R&D center where we are developing a metal hydride based hydrogen compression system. Now our target is that we want to achieve higher pressures in multiple stages. That is, research says that till 200 bar people have achieved in the metal hydride compression, and some research has gone up to 800 bar. However, these metal hydride compressors require sensible heating and cooling. So if we can integrate effectively the heat, that is a waste heat, into these systems, they will be working very fine. And what we want to do is, we have conducted the research experiments in our R&D center, which I will be presenting in the subsequent slides. And we want to scale up this system and demonstrate it on-site with the waste heat integration. Because nowadays people are talking about the solid oxide electrolyzers and the solid oxide fuel cells, which are also efficient when they are integrated well with the heat. So we are also trying to work on this kind of a system, and we are working along with IIT Bombay for this kind of work. I will just touch upon this concept wherein, what is a metal hydride? So metal hydride is a typical characteristic that requires a heat as well as a cold stream for effective absorption of the hydrogen as well as effective release of the hydrogen. So if you can see on the top, if absorption of a hydrogen on a metal hydride or a metal is exothermic. So we have to cool the metal hydride when the reaction happens. And if we want to get the hydrogen released from the metal hydride, we have to give a heat to it. So effective integration of this will be the crux of the development of the metal hydride compressor. Now if we see this figure, will just shows how the hydrogen gets absorbed on the surface of a metal. And from this, we see that if we have a different kind of metal hydrides, they have a different isotherms. When they have a different isotherms, you can achieve the pressures at a higher, almost people have gone to 800 bar. Only thing is, every metal hydride has a different isotherm. So this animation shows that how the hydrogen is coming and setting into the interstitial sites of the lattice. When we have searched what has happened with the globally demonstrated hydrogen compression systems, we have found very latest demonstrations happened in the past 3-4 years, globally in Switzerland, Africa. And you see these metal hydride compressors are used for low hydrogen flow rates, but they have gone to 250 bar as well, and the operating temperature is 150 degrees centigrade. Now in places like refineries and industries, there is process heat which is of 150 degrees centigrade. And people have used this system for hydrogen refueling stations, fueling the forklifts. So from this we got a clue that there could be the possibility that if a globe is working on MH system, Indian companies can also explore the potential of this. Getting a clue from this, at BPCL R&D Center, we started a modeling and we understood that the crux of this metal hydride compressor is how effectively you can do the heat transfer. And we know that surface area is the crux for the heat transfer. So we designed 2 different kinds of reactor, and in this we have shown that though this reactor is basically an embedded cooling tube reactor in which there are multiple tubes which are there into this. So from the center, from the top we fill the metal hydride which is in the powder form. From the center there is a heat transfer fluid which has to be hot and a cool. And this is a hydrogen in and hydrogen out. So what happens is when you are sending the hydrogen, and if you send a heat transfer fluid which is cooled stream of 5 degrees, 10 degrees, hydrogen will get absorbed into the metal hydride which is in this reactor. Similarly, we got these clues from the heat exchanger arrangements. And on the reverse side, if you have a tube bundle reactor wherein your metal hydride is filled in the tubes and your heat transfer fluid is going into the shell, and then again we see how the hydrogen is getting absorbed, then we did the reaction. Although the weight percent is on a lower side, subsequent experiments, we got a higher weight percent. But you see that embedded cooling tube is having a slighter better performance as compared to the tube bundle. But filling of the metal hydride in this arrangement is a tough, because this is the only way to fill the metal hydride and to remove the metal hydride. Based on this, we designed a scheme for a metal hydride reactor, and we developed a system at our R&D center, and we have done the trials in this reactor, and this is a heating and a cooling system. And you can see that this is a PCT of a typical metal hydride which we are working upon. We cannot disclose the composition as of now. However, you see the absorption is having in the range of 10 to 30 degrees. We give a sensible heating through the hot stream, then the desorption happens at a higher pressure. So in the subsequent slide, I will show that this is the absorption. So at a different supply pressure, we are having an electrolyzer at our R&D center, and we are producing hydrogen at different pressure rates, and we are using hydrogen, and we have seen that when your supply pressure increases for the metal hydride, your cooling requirement also increases. And we have seen that from inlet pressure of 10 bar, we have achieved the outlet pressure of 72 bar without any mechanical compression, and it is only with the help of metal hydride compression. And also see, when we see the benchmark comparison in the literature, this is one of the reference paper which I have taken 4 to 5 years before it published. What it says that for a similar amount of hydrogen production, that is 56 nm cube per hour, what crux is that you need a cooling water flow and energy is required. Otherwise, its annual maintenance cost is lower as compared to a mechanical compressor, and its capex is also slightly lower. So if we integrate it well with the heat, it will work. So subsequently, we are working on developing 3-stage metal hydrides. So what we really want to conclude is that it could be one green alternative to mechanical compressors, because we have the rotary parts, and again the bearings, seals are there. So it has to be coupled with waste heat, and the exothermic reaction heat from the solid oxide electrolyzers can be coupled to this metal hydride, and it could be an alternate solution to the mechanical compression. This is a food for thought, which I would like to say that if we connect it with solid oxide electrolyzer or fuel cell, it will be a good solution. Also, PEM fuel cells, which are generally used in the mobility application, they have a problem of the cold start. So if the cold start of the PEM fuel cell can be addressed, because we know that absorption reaction is exothermic in the case of metal hydrides. So we can supply this heat to the to the PEM fuel cell, and then we can circumvent the problem of cold startability in the fuel cell electric vehicle in a mobility. Also, globally people are using forklift which is hydrogen powered. Now forklifts are used not for the long ranges. So they don't want to store the hydrogen at a very high pressure. They can store the hydrogen at a lower pressure, do the forklift work in the warehouse, and can come back again for a refueling. So such kind of hydrogen compression requirements can be catered with this, because industry will be having a process heat. This process heat can be integrated into the MH compressor. You use it for forklift application. So this will be one of the sustainable solution for them. And also the microgrids in the remote locations. Because in the remote locations, again, putting the compressors, their maintenance would be a tough job, whereas remote locations, if we have a solar power or a solar thermal, we can harness that power also for metal hydride compressor. So way forward, what we are doing is, we are trying to work with multi-state reactors in a single setup, so that we can also achieve such high pressures, and also how effectively we can integrate the waste heat, so we can reduce the OPEX of our metal hydride compressor. This is all from my side. Thank you, sir.
Thank you, Rahul, for covering interesting topic related to metal hydride based hydrogen compressor system. Now, next speaker is Akshay.
A warm good evening to all of you, and my gratitude to the speakers before me. They made my task very easy. They have covered most of the basics. So before I start, I would like to start with a small story. So for some reason, Indra, the king of gods, decided to say that there will be no rain henceforth until Shiva plays the damaru. The damaru is a handheld small power drum. So what happens is, nobody prepares the fields, nobody prepares anything. People forget farming. But there's one guy who keeps on doing it. And seeing him, everyone starts to realize, oh, maybe we need to keep doing this so that we don't forget it. Eventually, just like how gods would have it, Parvati, the wife of Lord Shiva, says, hey, maybe you've forgotten how to play the drum. So this is it's in a very funny way that only a spouse can rebuke. She says, you've forgotten to play the drum. So just to satisfy his curiosity, he plays the drum, and it rains. And everyone that prepared got to see a bountiful harvest. Now, picture this story in the context of decarbonization. Every sector is pulling its weight, beyond its weight actually, to slowly and steadily decarbonize our energy and material supply chain. We dig deep and do our bit to get our energy supply cleaner and more sustainable. And in this analogy, the mother is science, and the father, or Lord Shiva, is the tax deduction of science, namely engineering science. So both of them combine to solve this puzzle of decarbonization. And the day science is merciful, we need to be ready to ensure that the engineering is set up to transform the science into a game changer technology. I'll start with a disclaimer. Any statement here is my personal view and does not represent the policy or the intent of Reliance Industries. The information presented here is my own, and in no way RIL attracts any liability or any inconsistency or irregularity in terms of accuracy, completeness, or veracity, the truth of the content, and it is assumed to be in good faith, and the content is the author's own mind. The scope of this presentation is strictly for knowledge sharing purposes and not necessary to provide any advice or recommendation to the audience or the readers. Any endorsement, recommendation, or suggestion made by the presenter or author, namely me, is in my personal capacity and not in any way and not in the professional capacity as an employee of RIL. Any person acting on such endorsement, recommendation, suggestion, or advice will be responsible for any injury and damage. I would like to introduce, most of you know, Reliance is one of the largest digital service providers. We are also deeply integrated in competitive positioning in terms of a very wide product portfolio. We are among the world's largest most integrated O2C business, including the world's largest single-site refinery at Jamnagar, and among the top 10 rankings in key products. We are also one of the most profitable retailers in India. We grow very fast, and we are now targeting an investment of close to $9 billion over the next 3 years to pursue opportunities in the new energy businesses. We have a plan to build gigafactories across solar, photovoltaic modules, energy storage batteries, and hydrogen electrolyzers, fuel cells, and power electronics. We are developing an enabling ecosystem of services across EPC and project financing to roll out close to 100 gigawatt near solar capacity by the year 2030. We are accelerating our transition from carbon fuels to a solar and hydrogen-based economy, and we are very well positioned to capture future growth opportunities. There are significant investments made by Reliance to help India and the world transition to clean and green energy. As you all know, as you've seen in the media, RIL has clearly declared that by the year 2035, we want to reach net carbon zero. We are one of the leaders in India in refining and petrochemicals, and we are also setting up in renewable energy, hydrogen, and power electronics. Now, hydrogen is a very key tool in the scope of decarbonization, where it can be used to drive the transition from fossil fuels to clean and sustainable renewable energy. But for hydrogen to be realized on a large scale, we essentially need to go through the bottlenecks, essentially addressing the problem of storage and transportation. Now, unless you can store and transport hydrogen safely, nothing that we say regarding the cost of production of hydrogen is going to make sense. So, in order to achieve this, the current standard of technology is storage in cylinders or composite cylinders. So, when you use cylinders as a part of the HRS infrastructure, you have pipelines, you have cylinders, you have chillers, you have compressors, and all these stages. But all of these need to work together in a safe manner in accordance with industry accepted standards so that you can design and optimize HRS operations to a good scale. And you need to ensure that you minimize your losses and maximize your value realization. When you talk about hydrogen refueling, one of the main components here, so you can see on the right, you have one of the HRS stations in Jamnagar, where we are experimentally trying out filling trucks which run on hydrogen. So the main components are essentially the infrastructure of the station, the original equipment manufacturers, the different components of theirs, the tank properties, and how each of these equipments communicate with each other. So for all this, you need large-scale field testing, and simulation of this filling and decanting process can essentially aid in accelerating the deployment at scale. Some of the key properties of hydrogen is essentially that it can be stored as a gas in an economical manner, and how economic is the definition for scale to scale. So when you take hydrogen, if you have to store it at standard temperature and pressure, it requires an enormous amount of volume. What I would like to convey here is hydrogen is only very good in terms of mass density. So you need to ensure that that particular angle is tweaked at. Safe storage of hydrogen under right conditions is a critical issue to resolve while addressing the possibility of a hydrogen economy. Why I am talking about hydrogen storage here is essentially, initially we had a lot of gasoline vehicles, and then came the wave of EVs. And now what we hope in the future can be the generation of hydrogen-powered vehicles. So if you can see, the performance of hydrogen is almost equivalent to that of EVs, with the capacity to refuel them much faster when compared to charging cycles, and having a higher range. To outline the problem, wherever you have hydrogen coming from, whether it may be green or blue or gray, or even green on a large scale production, or you have a small scale SMR unit, you're eventually going to have to compress it and then chill it and then send it into the cylinder which is located in the vehicle. For this, the hydrogen storage and transportation, we use generally compressed cylinders. It may be a single cylinder as in a vehicle, and it may be a cascade or a manifold-like structure for the station or in the logistical truck that brings gas to the station. While carrying out transfer of gas from one scale to the other, you need to bear two factors in mind. So anytime you compress the gas and you're going to fill it into a cylinder from a higher pressure to a lower pressure, there's always going to be an increase in temperature. And this increase in temperature is due to the Joule-Thomson effect and the heat of compression. When you fill the cylinder, you need to ensure that you are monitoring the temperature adequately, because if it exceeds a certain level, the integrity of the cylinder is going to be questioned. So it is essential to know what the temperature is while filling the gas. When you fill the gas, essentially what happens is you connect the fueling hose to the car, and you essentially have a pulse to check if the leakages are there or whether the contact is there. And then you start slowly ramping the temperature. When you ramp the temperature, it has to be done in a staged manner such that you ensure that the consistent flow of gas is there into the cylinder. At the same time, the temperature of the cylinder is under the integrity limits, and you have to ensure that your state of charge is reached. So for this, you need to ensure that there is no overheating or overpressuring, and there are no leaks. When you have to simulate this, essentially, we have used computational fluid dynamics to try to solve this problem and to get a feel for the numbers of how the temperature varies. So essentially, you have the orientation of the injector diameter, and the gas temperature at the inlet, and what the initial or ambient temperature conditions are. And regarding flow parameters, what the ramp rate will be, how you are going to increase the pressure into the cylinder. And what parameters are monitored is the gas temperature within multiple locations at the cylinder, the wall temperatures, the ambient temperature, and the total filling time. Now, simulation can be a great tool in essentially helping you figure out where the temperatures are high and where you would be better suited in positioning the probes to ensure that you have a correct picture. So when you go through essentially the problem, so you are essentially solving a complex heat transfer issue. So you have multiple layers of the cylinder, and in the center you have the pressurized hydrogen gas, which is essentially the source for the temperature. You have the inner liner and the outer liner, which is different materials depending on the type of the cylinder. And essentially your heat source is the Joule-Thomson effect and the heat that is dissipated from the compression losses. The operating conditions are essentially what the ambient temperature is and the gas temperature at the inlet. So our objective here will be to essentially monitor the temperature profile along the length and the radius of the cylinder at multiple locations. So for conditions, we will go through the filling rates. So you can go from low ramp rates to high ramp rates, and the dispenser pressure ranges. So what the mother cylinder's pressure is. So for 70 megapascal and 35 megapascal of daughter pressures, you have an 87.5 megapascal and a 43.8 megapascal mother pressures. The constraints are essentially what type of infrastructure you have at the HRS to ensure that you are able to fill cylinders continuously and in a safe manner. Your filling time should be restricted to 3 to 5 minutes. Your state of charge is essentially 90 to 100%, depending on how impatient or patient your customer is. Your gas cylinder temperatures, that is set in stone. You have to ensure that it is within the safe limit of operation. And your control factors are essentially what monitoring mechanisms you have to understand the tank pressure and its change dynamically, the pre-cooling of the hydrogen, how much energy you need to expend for that, and at what delivery rate you are giving the hydrogen, and how you decide when to terminate safely. We carried out the simulation for multiple conditions. For proprietary reasons, I cannot disclose the times. So you can see as the hydrogen gas enters, so from the right side of the cylinder it is entering, you can see that the temperature slowly sets off to increase. But because the source temperature is very low, it manages to cool the zone, but you have the hot zone developing at the end. And you have to take care to ensure that the gas cylinders do not reach a temperature of close to or greater than 85 degrees, because it will lead to material failure. In summation, I would like to say that green hydrogen holds a great potential in decarbonizing transport applications. You know that composite cylinders are used for the storage and transport, and this is especially true for onboard vehicle and refueling stations. Filling and decanting, high pressure operations, and you need to ensure that there is monitoring of the associated temperature rise. The process safety is critical. You have to estimate the cylinder temperature under the different conditions of filling. And here is where CFD simulations can hold a great potential in estimating the temperatures so that you know what to look for. When you are validating your simulation results against reported data in open literature, as well as against experiments that are carried out, you get more confidence in your simulation, and you're able to set up mechanisms on how to design these filling protocols, which are safe and compliant with the global standards of operation. If we ensure that we are able to solve this storage issue, it will be a small step towards realizing the hydrogen economy. But to paraphrase Neil Armstrong, it's a giant step in solving the problem of sustainable energy. So I would like to thank you for your patience, and I would like to thank IEW for the opportunity.
Thank you.
Critical one, sorry. I would like to acknowledge the partners in the study, GeoBP Gases, and the Tech COE team from RIL. And I would like to also thank the R&D team for the computational resources and the IP team for the clearance to give this presentation. And the list of references are provided. Thank you so much.
Thank you. Thank you. Thank you very much. It was a very exciting session. In a nutshell, there is no doubt that hydrogen is a very important vector of energy transition, and due to its low volumetric energy density, it offers several challenges. Speakers here have presented several views with respect to pipelines, with respect to compression systems, blending hydrogen into the natural gas pipelines. There are several technological advancements still awaited. There are many points to ponder upon. How this R&D can be further speeded up, how this research and how Atmanirbhar Bharat can develop these technologies. There are several other alternatives to look after. What about the liquid organic hydrogen carriers? What about making the TRL levels of these metal hydrides to a higher maturity levels, increasing the volumetric energy density of all storage options, availability of materials, practical delivery time for all the projects that we are facing, for the supply chain constraints. Nevertheless, there is some start to be given thanks to all the speakers expressing their views, and it was a very enlightening technical discussion, providing the perspective about the various challenges that are associated with the hydrogen storage and hydrogen transport related issues. And yes, thanks audience for a wonderful listening. So we come to end of this session. Thank you very much. Thanks all.